Hello everyone. The specific NEC rules regarding the connection of a grid interactive solar PV inverter to the electric grid can be challenging to understand at first and possibly fool you into thinking you understand them after you've learned the most obvious of them. But there's more to it than meets the eye at first. This document, that's intended as a guide for local building authorities in New York State, contains information that my town has incorrectly adopted in their solar permitting process. So I'm going to have to challenge the town's solar requirements to get my EG4 18 kPV hybrid inverter online with a permitted and inspected design. The highlighted line here will need to be rewritten or accepted if I'm to get my system installed the way it correctly should be. It says, some of the main overcurrent protective device and the inverter overcurrent protective device is rated for not more than 120% of the busbar rating. That's not what the NEC says about that topic, so it needs correction. But the EG4 18 kPV is also an exception to that rule per other NEC rules. Let's take a look at this. I plan on keying my wiring design off of EG4's example wiring diagram from the installation manual. Here it says the NEC code formula for working with backfed breakers is as follows. The sum of the main service breaker plus 125% of the inverter output rating cannot exceed 120% of the busbar rating on the breaker panel. To support that, it refers us to the 2020 NEC code article 705.12b3. Let's take a look at 705.12b3. The problem is that's the wrong code reference. I think the code reference they're looking for is 2026 705.12b2. Let's look at 705.12. 705.12 Load side source connections. The output of an interconnected electric power source shall be permitted to be connected to the load side of the service disconnecting means of the other sources at any distribution equipment on the premises. This is the pertinent part of that big wiring diagram I displayed a minute ago. This is the 18 kPV hybrid inverter. This is the main service panel in a residence. Here's the service meter. This is the feeder from the inverter to the main service panel and vice versa. So all this is saying is that you can connect the output of an inverter to a load center's circuit breaker bus. That's the load side of the main breaker. The source side is the grid side of the main breaker. Next sentence. Where distribution equipment or feeders are fed simultaneously by a primary source of electricity and one or more other power sources, the feeders or distribution equipment shall comply with the relevant sections of 705.12a and b. The primary source of electricity is the utility grid. And this says if there's one or more solar inverters connected to your service as well, all that equipment must comply with the relevant sections of 705.12a and 705.12b. Currents from power source connections to feeders or bus bars shall be based on the maximum circuit currents calculated in 705.28a. The ampacity of feeders and taps shall comply with 705.12a, and the amperage ratings of bus bars shall comply with 705.12b. Let's look at 705.28a first. A. Power source output maximum current. Where not elsewhere required or permitted in this code, the maximum current for power sources shall be calculated using one of the following methods. There are three possible methods. 1. The sum of the continuous output current ratings of the power production equipment at the circuit nominal system voltage. So add up the continuous output current ratings of all the inverters. Note that continuous means multiply that by 125%. 2. For power production equipment controlled by an EMS, the current set point of the EMS. An EMS is an energy management system. The energy management system this refers to monitors the current at the source side of the main breaker and modulates the inverter output accordingly. So if there's high current being drawn from the grid, the inverter output is reduced to prevent the panel bus from being overloaded. The plot thickens. 3. Where sources controlled by an EMS are combined with other sources on the same power source output circuit, the sum of 705.28A1 and A2. If there's an EMS-controlled inverter on the same circuit, the current set point of the EMS is added to the continuous output ratings of the other inverters. Okay, back to 705.12a, feeders and feeder taps. Where the power source output connection is made to a feeder, the following shall apply. 1. The feeder ampacity is greater than or equal to 125% of the power source output circuit current. So the ampacity of that feeder has to be rated at least 125% or more of the maximum rated output of the inverter. Okay, 2. Where the power source output connection is made at a location other than the opposite end of the feeder from the primary source overcurrent device, that portion of the feeder on the load side of the power source output connection shall be protected by one of the following. Clear enough, isn't it? I'm not well versed at interpreting this section of the code, but I think I've got a pretty good handle on it. However, if you have something to add, please do so in the comments below. In the case of my system, it really doesn't affect anything since it doesn't apply. I'm not using a feeder like this. I think this is the scenario we're looking at. Bear in mind, this is feeders and taps, where the power source output connection is made to a feeder. So my diagram shows a feeder that's supplying an existing subpanel. Pretty standard stuff. Except now Mr. Solar Installer is tapping the output of the inverter into that feeder to send it to the grid. The feeder ampacity must be equal to or greater than 125% of the power source output circuit current. So where the power source output connection is made at a location other than the opposite end of the feeder from the primary source overcurrent device, that portion of the feeder on the load side of the power source output connection shall be protected by one of the following. 705.12a2a. The feeder ampacity shall be not less than the sum of the rating of the primary source overcurrent device and 125% of the power source output circuit current. This is actually very straightforward. That portion of the feeder, shown in extra thick lines, on the load side of the power source output connection, is protected by, in this example, take 125% of the inverter output current and add it to the primary source 100 amp overcurrent protective device. The feeder needs to be rated at that ampacity. Lowercase b. An overcurrent device at the load side of the power source connection point shall be rated not greater than the ampacity of the feeder. So I'm a little hazy on this, but it appears this is what they're looking for. (705.12a3). For taps sized in accordance with 240.21b2 or b4, the ampacity of tapped conductors shall not be less than 1/3 of the sum of the rating of the overcurrent device protecting the feeder, plus the rating of any power source overcurrent devices connected to the feeder. If you're not familiar with taps, I published a video about the 25-foot tap rule that will get you up to speed. That's what 240.21b2 defines. I grayed out the text referring to B4 because I'm considering it outside the scope of this video. In this example, the tap conductor ampacity is greater than or equal to 1/3 of the sum of the rating of the overcurrent protective device protecting the feeder, plus the rating of the power source overcurrent protective device connected to the feeder. So here's a question for you. What's the gauge size of the tap conductors in this example? Moving on to the bus bars, which is the actual topic of this video. It might be obvious, but these are the bus bars in this diagram. The purpose of this code is to prevent the bus bars and load panels from being overloaded. Too much current passing through the bus bars can cause them to overheat. If the overheating is excessive, the copper or especially aluminum bars can become damaged and fail, possibly even causing a fire. I've seen this happen with aluminum bus bars, which only caused a power failure in the house. It required installing a new main panel to fix it. 705.12b Bus bars. For power source connections to distribution equipment with no specific listing and instructions for combining multiple sources, one of the following methods shall be used to determine the required ampere ratings of bus bars. 1. The sum of 125% of the power source's output circuit current and the rating of the overcurrent device protecting the bus bar shall not exceed the bus bar ampere rating. And there's an informational note to go along with that. Informational note. This general rule assumes no limitation in the number of loads or sources applied to bus bars or their locations. So this one's very straightforward. Add the rating of the main breaker to 125% of the ratings of the other power sources, say one or more inverters, and that's the minimum the bus bars must be rated for. In this case, the bus bars would have to be rated for 288 amps, which they obviously wouldn't be in the average 200 amp service. So this is a no-go. But wait, there's more. 2. Where two sources, one a primary power source and the other another power source, are located at opposite ends of a bus bar that contains loads, the sum of 125% of the power source's output circuit current and the rating of the overcurrent device protecting the bus bar shall not exceed 120% of the bus bar ampere rating. The bus bar shall be sized for the loads connected in accordance with Article 220. A permanent warning label shall be applied to the distribution equipment adjacent to the backfed breaker from the power source that displays the following or equivalent warning. Warning: power source output. Do not relocate this overcurrent device. The warning signs or labels shall comply with 110.21b. Of all the options, this one appears to be the most applicable for the average installation. We'll take a deeper look at this one later in the video. 3. The sum of the ampere ratings of all overcurrent devices on panel boards, both load and supply devices, excluding the rating of the overcurrent device protecting the bus bar, shall not exceed the ampacity of the bus bar. The rating of the overcurrent device protecting the bus bar shall not exceed the rating of the bus bar. Permanent warning labels shall be applied to distribution equipment displaying the following or equivalent wording. Warning: equipment fed by multiple sources. Total rating of all overcurrent devices, excluding main supply overcurrent device, shall not exceed ampacity of bus bar. The warning signs or labels shall comply with 110.21b. So with this option, we'd add up all the circuit breaker ratings on the bus bar, and as long as the total doesn't exceed the bus bar rating, we're good to go. As long as the bus bar is protected by a main breaker that corresponds with the rating of the bus bar. This wouldn't work for many or most main service panels. If you have just 10 20 amp breakers in a 200 amp panel, there's no capacity available to add an inverter. The only place I might consider using this option is on the house meter of a multi-unit dwelling. Some jurisdictions require landlords to have an extra service on multi-unit dwellings, called a house service. The house service provides just general lighting for hallways and outside the dwelling, maybe the basement, and smoke alarms for the building. The idea is that tenants shouldn't have to pay for those loads. City governments are run by silly people who don't understand that landlords will simply increase the rents to cover that expense, so they aren't saving anyone anything. But I digress. We'll jump over to 110.21b momentarily. 4. A connection at either end of a center-fed panel board in dwellings shall be permitted where the sum of 125% of the power source output circuit current and the rating of the overcurrent device protecting the bus bar does not exceed 120% of the busbar ampere rating. I'm not using a center-fed busbar, but it's handled just like an end-fed busbar. The solar inverter has to be connected at either end of the busbars. 5. Connections shall be permitted on busbars of panel boards that supply lugs connected to feed-through conductors or are supplied by feed-through conductors. The feed-through conductors shall be sized in accordance with 705.12a. Where an overcurrent device is installed at either end of the feed-through conductors, panel board busbars on either side of the feed-through conductors shall be permitted to be sized in accordance with 705.12b1 through b3. This isn't your average residential configuration, so it's outside the scope of this video. 6. Connections shall be permitted on switchgear, switchboards, and panel boards in configurations other than those permitted in 705.12b1 through b5, were designed under engineering supervision that includes available fault current and busbar load calculations. Informational note: specifically designed equipment exists, listed to UL 1741, inverters, converters, controllers, and interconnection system equipment for use with distributed energy resources, for the combination and distribution of sources to supply loads. The options provided in 705.12b are for equipment with no specific listing for combining sources. My EG418 kPV application doesn't require a configuration other than those permitted in 705.12b1 through b5. And most residential inverters don't. So this is outside the scope of this video. Okay, as promised, 110.21b, Field Applied Hazard Markings. Where caution, warning, or danger hazard markings such as labels or signs are required by this code, the markings shall meet the following requirements. 1. The marking shall be of sufficient durability to withstand the environment involved and warn of the hazards using effective words, colors, symbols, or any combination thereof. Informational note number 1, see ANSI Z 535.2-2011 R 2017, Environmental and Facility Safety Signs, which describes the design, application, and use of safety signs in facilities and in the environment. Informational note number 2, see ANSI Z 535.4-2011 R 2017, Product Safety Signs and Labels, which details the design, application, use, and placement of safety signs and labels on a wide variety of products. 2. The marking shall be permanently affixed to the equipment or wiring method and shall not be handwritten. Exception to 2. Portions of the markings that are variable or that could be subject to changes shall be permitted to be handwritten and shall be legible. I'm not going to try to go through all these label and sign requirements here. Suffice to say, there are standards our labels are required to conform to. There are several pre-made label packs on the market to help us comply with these marking requirements. This example wiring diagram from the 18 kPV manual is a helpful guide to wiring your system. This represents the section of that diagram where the main panel bus bars are located. Let's revisit 705.12b2. 705.12b2 starts out saying, where two sources, one a primary power source and the other another power source, are located at opposite ends of a bus bar that contains loads, the sum of 125% of the power source's output circuit current and the rating of the overcurrent device protecting the bus bar shall not exceed 120% of the busbar ampere rating. The primary power source is the service main breaker. The other power source is the inverter circuit breaker. And like it says, they're located at opposite ends of the busbar. The sum of 125% of the power source's output circuit current and the rating of the overcurrent device protecting the busbar shall not exceed 120% of the busbar ampere rating. So we're adding the main breaker rating to the maximum inverter output rating times 125%, like this. It turns out 120% of 200 amps is 240 amps, which is 23 amps less than the sum of the combined power sources. So this configuration can't work. And does it make a difference that I want to use a 100 amp circuit on the output of the other power source? The maximum output of the 18 kPV is 50 amps, so I don't think the larger circuit capacity makes a difference as far as busbar loading. However, I want the larger capacity for use in charging the battery bank while simultaneously supplying the critical load panel loads. Moving on, that's really the minimum busbar sizing loads calculation, but check out my video about code-based residential load calculations to see how to do that for a new system. Let's review these numbers again before discussing what we're going to do about it. We have 200 amp bus bars in the panel, and the maximum inverter output is 50 amps to the grid. Multiply 50 amps times 125%. Add them up and we get 262.5 amps. Take the 200 amp bus bar capacity and multiply it by 120%. That comes to 240 amps. Our load needs to be equal to or less than 240 amps. 262 amps clearly exceeds 240 amps by a significant amount. So this configuration is out of compliance with 705.12b2. What's behind all this? Imagine if you had bus bars with loads on them exceeding their rated capacity. Like if everything here was running at its maximum amperage. These circuit breakers add up to 368 amps. When you add the 200 amps coming from the grid with the 50 amps coming from the inverter, there's certainly a possibility here of overloading and overheating these bus bars, which are rated for 200 amps. Also bear in mind that the 200 amp bus bars can't be continuously loaded at greater than 80% of their capacity. The continuous load rating on these bus bars is 160 amps. So, what can be done to bring this into compliance? One option is to replace the main service panel with one of the available 225 amp load centers, then provide it with a 200 amp main breaker. Because 225 amps times 120% equals 270 amps, which is greater than our 262.5 amp target. So, this will work. The EG418 kPV manual wiring diagram 4.1 includes a table showing some of the possible options. Here's our non-compliant 200 amp bus with a 200 amp main breaker. And here's our 225 amp panel bus bars with a 200 amp main breaker. Notice the green check at the bottom of the column. There's also a note at the bottom stating that the inverter breaker must be at the opposite end of the bus from the main breaker. Another option shown is to reduce the rating of the main breaker. As this column indicates, the 18 kPV can share 200 amp bus bars with a 175 amp main breaker. But as we've covered before, that main breaker must conform to the loads connected in accordance with Article 220. So you'll need to perform a code-compliant service load calculation, like this. And your AHJ should want to confirm that's done correctly. Notice that my calculation justifies the use of a 150 amp main breaker. And that's what I was planning to use. More about that coming up, because there's a new twist to all this. We need a little housekeeping before moving forward with that twist. NEC 705.30 overcurrent protection. 705 is for interconnected power sources. B. Overcurrent device ratings. The overcurrent devices in other than generator systems shall be sized to carry not less than 125% of the maximum currents as calculated in 705.28a. The rating or setting of overcurrent devices shall be permitted in accordance with 240.4b and c. We'll take a look at 705.28a shortly. There's an exception. Circuits containing an assembly together with its overcurrent devices that is listed for continuous operation at 100% of its rating shall be permitted to be utilized at 100% of its rating. C. Marking. This goes hand in hand with the labeling and marking we reviewed in Article 690. Equipment containing overcurrent devices supplied from interconnected power sources shall be marked to indicate the presence of all sources. D. Suitable for backfeed. Fused disconnects, unless otherwise marked, shall be considered suitable for backfeed. Circuit breakers not marked line and load shall be considered suitable for backfeed. Circuit breakers marked line and load shall be considered suitable for backfeed or reverse current if specifically rated. The helpful takeaway here is if your circuit's breaker isn't marked for line and load, it's suitable for backfeed use. E. Fastening. Listed plug-in type circuit breakers backfed from electric power sources that are listed and identified as interactive shall be permitted to omit the additional fastener normally required by 408.36d for such applications. For example, portable generator backfed breakers are required to be fastened in place, the theory being that someone could remove the backfed breaker while it's actually energized and get shocked, or worse. But solar inverters that are listed and labeled as grid interactive will shut down within 1 or 2 cycles, so that circuit won't be energized if someone pulls it hot. They shut down within milliseconds, so they don't present a shock hazard. On to 705.28a. Circuit sizing and current. A. Power source output maximum current. Where not elsewhere required or permitted in this code, the maximum current for power sources shall be calculated using one of the following methods. 1. The sum of the continuous output current ratings of the power production equipment at the circuit nominal system voltage. So just add up the current outputs of all the power sources to determine the maximum current for power sources. 2. This is where the plot thickens. For power production equipment controlled by an EMS, the current set point of the EMS. An EMS is an energy management system. It's an electronic control system that tracks the loads and current output of the system and automatically limits the output current of the source. In this case, the inverter output is limited. 3. Where sources controlled by an EMS are combined with other sources on the same power source output circuit, the sum of 705.28a1 and a2. In other words, in cases where there's multiple power sources, the currents from the non-EMS power sources are added to the currents from the EMS power sources to obtain the maximum current for power sources. We'd then be required to multiply that by 125% when we're calculating busbar loading. Sorry, I'm jumping around a bit and I got this out of order. 705.13 Energy Management Systems, EMS. An EMS in accordance with 750.30 shall be permitted to limit current and loading on the busbars and conductors supplied by the output of one or more interconnected electric power production or energy storage sources. Informational note. A listed power control system, PCS, is a type of EMS that is capable of monitoring multiple power sources and controlling the current on busbars and conductors to prevent overloading. PCS is Power Control System. CUL 1741, Inverters, Converters, Controllers, and Interconnection System Equipment for use with distributed energy sources. And UL 916, Energy Management Equipment for information on PCS and EMS. Article 750 covers energy management systems, and 750.30, which was previously mentioned, covers load management. 750.30 Load Management. Energy management systems shall be permitted to monitor and control electrical loads and sources in accordance with 750.30A through C. C. Capacity of branch circuit, feeder, or service. An energy management system shall not cause a branch circuit, feeder, or service to be overloaded. If an EMS is used to limit the current of a conductor, 750.30C1 through C4 shall apply. 1. Current set point. A single value equal to the maximum ampere set point of the EMS shall be permitted for one or more of the following. 1. For calculating the connected load per 220.70. 2. For the maximum source current permitted by EMS control. So a single set point in the EMS can control the maximum ampere set point of the source current. And here's the twist. Let's zoom in on this section of EG4's diagram 5A, 18 kPV with backfed breaker, busbar PCS, and partial home backup with notes. EG4 hybrid inverters are now UL listed for busbar PCS, which allows a backfed breaker to be sized larger than the 120% rule that we just talked about. By utilizing an energy management system, EMS, or more commonly known as PCS, see 2023 NEC 705.13, we just looked at that. For PCS to work properly, the CTs must be located on the utility side of the main breaker, protecting that bus bar as shown. CTs are current transformers. The 18 kPV has power control system functionality built in. There's a pair of CTs, also known as current transformers, that are used to monitor the current flow on the supply side of the main circuit breaker. The CTs look very similar to these. The power control system monitors the current on the supply side and internally on the grid connection. The PCS functions protect the bus bar by combining monitoring from the CTs for your grid current and the internal EMS to limit the amount of export power. When the bus bar comes within 80% of your PCS set point, the inverter will gradually reduce the amount of export power to protect your bus bar. Ultimately, if there's 200 amps or whatever the adjustable set point dictates coming in on the main breaker, the inverter will be exporting 0 amps. I'm thinking I want my set point to be 160 amps. That's a number that will be very safe and maintain all my energy needs at the same time, because the inverter will start down modulating at 80% of that, or 128 amps, which my system will never be consuming anyway. With this system in place, there's no need to upgrade a 200 amp main panel or derate the 200 amp main breaker. Based on my town's PV permit application, I'm going to have to educate the building inspector and possibly the electrical inspector by covering all this material with them. Maybe I should just simply ask them to watch this video before they're evaluating my permit. Thank you for watching. Please take a moment to like and subscribe.